There's a differential equation. What order differential equation is this? First order, yeah. Only got dy by dx in it, not the second differential. And you solve it by separating the variables. So have a go at it. I'll pause this video and then have a go at it, and then we'll look at it. So to separate the variables, just to get going here, what do we do? So I'm going to leave dy on the left and dx on the right. So I'm going to shift the dx over here. So that means I want to get all terms involving y on the left hand side and all terms involving x on the other side. So I'll get y, leaving that on the left hand side and then dividing by y squared minus 1, dy equals 1 over 4x, or 1 over 4x dx. I could leave the 4 on the left hand side if I wanted to. It doesn't matter what I do with that constant 4, but that's probably as good a way as any. So I've separated the variables now. All I need to do is integrate both sides. And as a bit of a hint, this side is going to involve using algebraic substitution, this idea, remember, that we talked about before. And this side, separate out the quarter from the x bit. And so you can see what that is, hopefully. So have a go at that. I'll pause it at this point. See if you can integrate those two sides. So looking at the right hand side, the integral of the right hand side, if we think about this as 1 over 4 times 1 over x dx, that will help us, won't it, separate out the quarter from the x. And for this one, if I let u equal y squared minus 1 and then differentiate that with respect to y, I can then use substitution. So dy equals du over 2y, and I can substitute that in, and you see that the y's disappear. If you think back to last week, we know that it's going to work because the differential of this is y, so it's going to cancel the top. Remember, the top needed to be the differential of the bottom for the algebraic substitution to work. So I can now go ahead and do it. So on the left hand side I'm going to get y over y squared minus 1 du over 2y equals a quarter 1 over x dx. So now I just integrate both sides. Of course I'm replacing this with u, which u equals that. So I end up with a half log u, which is y squared minus 1, equals a quarter log x plus c. Just add one c right at the end, and that's my solution. So this is our implicit solution. Implicit. Because it's not explicitly in terms of y. You could find out what y was, but it's involved. Y is in there, but it's not explicitly y equals something. So it's an implicit solution. It's correct, that is the general solution. General because We don't know C, and in fact in this case we can't find C because we're given no initial conditions. But what we can do is go further and try and write down what the explicit solution is using these rules of logarithms that we were talking about. So to start thinking about this explicit solution now, what I need to do is have logarithms just on both sides, so then I can find e to the power, and that will get rid of the logarithms. So I need just like one term on both sides, and then I can finish off by doing e to the power both sides, and that will get rid of the log. So the first step is to try and think of this differently, which is what we were sort of talking about in last week. If I think of C, instead of C as log, another constant, log A, I can include that in here. So I can think of this right-hand side as being a quarter log x plus log A, some other constant. It's still a constant, it's just now in terms of a natural logarithm. And then I can think of the laws of logarithms that tells you I've got log of one plus log of another. That's the same as log of x times a. So I can actually now say this equals a quarter times the log of x a. And I could separate them out, couldn't I? Oops. Yeah. A quarter. I've got to be a bit careful there because of that quarter, actually. Yeah. I think I need to. I was going to leave that step till next, so let me just think again about that. Let's get rid of these fractions. If I multiply both sides by 4, I get rid of that quarter on this side and I turn that to a 2 over here. So 2 log y squared minus 1 equals log x plus log a. Again, the fact that it's 4 times log a doesn't matter, it's just a constant, so let's call it log a. That makes it look a little bit better. Remember, the law of logarithms tells us the log of something times something is the same as the log of y squared minus 1 to the power 2. So I can write this as log y squared minus 1 to the power 2 equals log of xa, combining them together. So what I've done here is I've used laws of logarithms to get the left-hand side just as the log of something and the right-hand side as the log of something. So the whole point of doing what I did was to get rid of this 2 here and this extra term, this plus log a, by using the laws. You see what I've done there? So now I can just say take the e to the power of both sides, and that will get rid of this log, and I can say that y squared minus 1 squared equals xa. If the log of y squared minus 1 squared equals the log of xa, then y squared minus 1 squared equals xa. They're effectively gone. Two times the log of something becomes the log of y squared minus 1 squared, so that 2 in fact goes up there.
That notation, is that the log of what's in the...
The law we're using is this one. Log of x to the power a is equivalent to a times log of x. Log of x to the power something is the same as that power to the log of x. So that's what I've done here in reverse, effectively, to get to here. So now I can rearrange this little equation to get y, if I wanted to. I'll leave that there because that's quite a few steps involved with that, and it's not, I want to move on, but. So now I can rearrange this little equation to get y, if I wanted to. I'll leave that there because that's quite a few steps involved with that, and it's not, I want to move on, but. what I wanted to do with this one was to look at what we do with these logarithms, which is something that we were thinking about last week, wasn't it? So that's another example of that.